Hello everyone and welcome to another episode of Solving Advent of Code on Rust and trying to learn Rust in between. I'm Roberto and we have
Luciano. Hello.
Thank you everybody for following along. If you never did Advent of Code is a code challenge that is published every year around the Christmas period. We are working toward the last year one. There are 24 challenges and you can find them on adventofcode.com. We are publishing all our code on GitHub. We have our YouTube channel where we publish all the recordings. You can find the link in the description of the Twitch channel. Last time we finished to solve exercise 22. That was 22, the one about the one about the cubes, adding and removing cubes to the reactor for the Santa Claus submarine to retrieve the keys. So now we are going exercise 23. Who's going to read the readme?
I can try.
Do you have it ready?
I guess. Give me a second that I can open it. So let me switch scene and screen. All right, so day 23 is called amphipod. I guess that's how you read it. And it's a new type of animal that looks like a shrimp to me. If you want to see it, it's like this guy here.
Yeah, seems a shrimp, yeah. I don't know how big, but...
How do you go back without the navigation bar?
Command left.
Next time.
Next time.
Good to know. Okay, so we have these little animals and we meet them in the ocean with our submarine while we do things. That's the common theme of Advent of Code 2021. And they are basically giving us a challenge. We need to help them solve a particular problem. And the problem is basically like a simulation game on a board with very specific rules. And we'll need to figure out what's the most efficient set of moves for that particular configuration that we get. I'm giving you a spoiler, but just so that everything it's a little bit easier to understand because I don't want to read every single detail here. So basically there is like a cave where all these amphipods live, and there are 4 different kinds of amphipods. I'm going to just call them animals because I cannot pronounce that. So there are 4 different kinds of these animals depending on their colors. So we have amber, which is marked with an A, bronze, which is a B, copper, C, and desert, D. So A, B, C, D. And they live in this cave. And this cave has a very particular configuration. There is a hallway, and then there are side rooms. And you can see here that there is a little bit of a graphical visualization of that. So this is basically the hallway. And then here where you see B and A, or C or D, B or C, and so on, these are like vertical rooms. So this is basically a starting configuration. They call it situation, our puzzle input. So our input file literally looks like something like this.
Yep.
And this is basically where the amphipods are living. Now, they think that they are not organized because they are kind of randomized in the rooms, and they would like them to be more organized. So they will want to have all the amphipods with an A in the first room, all the ones with a B in the second room, all the ones with a C in the third room, all the ones with a D in the fourth room.
In the meantime, we greet Tommaso that is in the chat, and we have a new follower, Code for Real 1.
Oh, hello, Tommaso, and thank you, Code for Real, for following us. How are you doing today? And say hello in the chat. We'd love to know more from you. So
they are in random positions, and they want to go in the final configuration that is a more sorted and less chaotic configuration.
Exactly. Now, you can imagine that in order to go from here to here, they need to move around. And this is like a board game where they cannot overlap and they cannot kind of jump over each other. So you need to kind of calibrate all the movements in such a way that you have enough space for them to kind of rearrange. And of course,
like a little bit like the Hanoi towers that you have to move
exactly.
The circles with rules, and you have to go to the final configuration with everything sorted out. This is more or less the same, but with different rules.
Yeah. And so of course, the idea is that we'll need to figure out what is the sequence of movements that we need to come up with to have a sorting. And of course, there will be multiple solutions. So there are additional rules so that we can figure out which one is the most optimal solution. And the idea is that every movement costs some amount of energy, and the amount of energy depends on the type of animal or amphipod that we are trying to move. And it's basically the A ones require 10 energy for every movement. The copper ones, 100, desert one, 1000, and the amber ones is 1. So A is 1, B is 10, C is 100, D is 1000. And also every single cell that they move, they spend as much energy as per their type.
Yeah, every step that they do is costing n energy based on their type.
And we have some examples here. So for instance, here there is a like step-by-step example. So they start by taking this particular B here and moving it here. So that basically means that it was here. So it did one step, a second step, a third step, and a fourth step. Now B costs 10 for every step. So basically, because we did 4 movements, this should be
40.
There it is. I was looking at 400 and I was like,
no, 400 is for the copper.
This is the next step. Yeah. In the next step, what they do, they move C from here to here, because this way they already ordered the C column. So C is doing 1, 2, 3, and 4 movements, and C costs 100 per step, so it's 400 energy. So far we have been spending 400 plus 40, 440 energy. So we need to keep going until we end up with a final configuration where basically we have AA, BB, CC, DD. And at that point, we have summed all the energy, and we know how much energy did that particular solution cost. And of course, if we simulate all the possible movements, we take all the ones that lead to a final solution. We know at that point which solution is the most cost efficient. And this is basically what our part 1 is asking us. What is the solution that costs the less? So we have a question from Tommaso saying, why is this not displaying on screen?
Twitch magic.
There you go. So you need to create a graph of all possibilities of movements, create an heuristic function, and visiting that graph, finding all solutions, and check which consumes less energy. Exactly that, yes. And basically, I'm going to give a spoiler on part 2 as well, because it's literally the same problem. The only difference is that the board is a little bit expanded. So rather than caves being of size 2, there are 2 additional lines that gets added between line 1 and the first line and the last line. And so, of course, the sorting, it's more complicated because you need to arrange things, considering that the caves needs to be filled with more depth, basically. So, yeah, there is a little bit more space, I guess, to consider. So this will be the final solution for the part 2. But the ask is the same. Like, what is the solution with the cheapest cost?
Yeah, and here in the README, they drive you through all the movements. So if you want to take a look at the README, there is a lot.
So that's basically it. I don't know if it's clear. If it's not, feel free to ask questions and we'll go through it again. But I know that we have a Python solution. So Roberto, do you want to go through it?
Yeah.
And by the way, we don't have a Rust solution. So today we're going to try to write it from scratch.
We have to start from scratch, yeah. Will be very funny. So input is our input. So our input is a multi-line string with the input of with the chew, depth chew. Then this is just how I parse the input. It was a try to a test to understand how to parse it. Basically, I can show you what is coming out of this. When I take, what I'm doing, I'm taking the input, splitting the input by lines, rotating them with the zip. So I will find the same input, but rotated. At that point, I'm taking this AD is my first AD here. The CD is this CD, BB is this BB, and AC is the last one. So I know that is of this list is position 3, 5, 7, and 9. And the cells are 2 to 4 excluded, because Python is excluding the number of the right. So it's AD, CD, BB, and AC. And basically, just like this, I did the parsing. And here I tested
just to understand, the split lines gives you what? An iterator for every line?
Split lines gives you, in Python 2 was giving you a list. I don't know if it's giving you an iterator now in a generator now in Python 3, because they changed a lot of stuff to be generators. No, it's still giving you.
Okay, so you use the asterisk to basically spread that into a zip. So yes. Zip creates a
rotated version.
Okay, and then you use list to materialize the zip.
Yes, I get the amount of the zip. Here I don't have 2,4 because I wanted to have the full line in that one. But if you do this, this is the first hole, the first borrow, the second hole, third hole, and fourth hole.
Okay, yeah.
And the one on the left is the one facing the hallway, and the one on the right is the one not facing the hallway, so the one facing the bottom of the pit.
I have no idea how to do the same in Python, but I like it. What you did
in Rust, you mean?
In Rust, yes. I like what you did in Python. Yeah.
We have to parse the input somehow.
Yeah.
So my Python solution, let's see. Costs is just a map of the cost between the type of amphipod and the number. So type of animal and the cost. This is a map between where the animal want to go. So A wants to go in 2, B wants to go in 4, C wants to go in 6, and D wants to go in 8. I'm numbering by this way. So 0, 1, 0 is here, 1 is this one, and 2 is this one. So the X that the amphipod wants to go is 2. Then it's 4, 6, and 8.
I'll stop you there for a second. But first of all, can you zoom a little bit? And then second, we have a comment from W. Gaffa, who is very excited for writing Rust from scratch.
Cool.
So, yeah, hopefully you can help us because this will be tough.
Yeah, instead we are very worried, but everybody is taking the life as they want. So I was saying, it's better now with the font size?
Yeah, thank you. I think it's more readable to me.
Then I kept a list of I called them parking spot, even if they are the all-way slots. I didn't put 2, 4, 6, and 8 because there is a rule that say that they never stop in front of a hole. If they are in front of the hole, they want to go inside. So
I forgot to mention that. Yeah, that's a good point.
When they are inside, they go outside, and when they are outside, they go inside. But when these are the allowed position outside of the holes.
So basically, they never block the entrance to.
They never block an entrance. Yeah. Then I defined a class called board. That is our board. Let's call it board. If we want to call it board, is our state, is our something. Start is the input. We have the holes. We have the borrow. That it is a map of A to an empty list, B to an empty list, C to an empty list, and D to an empty list. Watch out. This ABCD is not the animal itself. It is a label to the hole where A wants to go. So A wants to go in this list, B wants to go in this list, C wants to go in this list, and D animals wants to go in this list. Then I have my 11 slots of parking with known in all of them. I will never use 2, 4, 8, and 6, but I'm creating them anyway, so it's easier to address the vector. The cost of this board is 0 because no movement made, no cost paid. If I have an input I do this because when I'm doing the move, I'm going to create a board without anything inside. I'm doing what I showed you before. I'm rotating the input. I'm computing its depth. This solution is working for part 1 and 2. So this depth will contain 2 if the input is made from the input of part 1. It will contain 4 when we will do that with the input of part 2. It is basically the length of any row minus 3 because we have a free character, the whole way, the wall and the wall on the other side that are not to take in account. Then ABCD is the animals in the hole A, the animals in the hole B, the animals in the hole C, 1 and D. They go in their hole with this. They go in the map that is created in this line. And this is our parsing initial state of the board. Now, utility function is final. Is final means that all the holes have length depth. So there is 2 animals in every hole. And all of the animals are of the type of animal that must be in that hole. So in the hole called A, there are only animals of type A. In the animals in the hole with the KB, there are only animals of type B, and so on. And the depth is the right depth. So this is basically how do we determine that a board is not going to evolve anymore. Moves. Moves is a function of this class that is giving me back all the possible valid moves that can be made. So I created commands in Python as strings because I'm always lazy. So instead of having an enumeration like we will do in Rust of a type command that can be going inside or going outside of a borrow, and an integer that's probably will say from this borrow to this parking position and from this parking position to this borrow. So in Rust probably we will implement it like that. I implemented a string of length 3, always length 3. And I was able to represent all the possible moves that are from a borrow to a parking position to the hallway, and from the hallway back in a hole. Here I have 2 different loops. The first loop looks at everything that can come out of a hole and can go to the left, and where it can go on the right. Every time I find something that I can do, I do IELD. So this is a generator. In Rust, we could do a vector and return a vector with all the moves, or do
or use the generator create.
Yeah, but to start with, we can use the vector also because it's the first state that is probably the one with most moves, as 27, in the order of 30 or something moves. It's not a lot. So it's not thousands of moves also because the board is very small. So from inside every hole, to the left of the hole and to the right of the hole, obviously, if there is something in the parking, in the hallway, that stop us, we break, because it means that we can't go after that animal. Then I'm looking for all the possible moves that something in the parking spot, something in the hallways goes into a hole. But for rules, they go in a hole only if the hole is empty, or if all the animals in the hole are already of its own type. And if there is not, if somebody between them and the hole, because if they are in the hallway and there is something in between them and the hole, they can't go in, because again, they can't pass through people and they can't jump above.
Meanwhile, we have Mika Dev that just followed us. So thank you very much. Welcome to the stream. And yeah, I'm interested to know, are you learning Rust or just stumbling here by coincidence?
Between is just a help function to be able to go to give slices if A is greater than B or B is greater than A, because when we have an hole, we have the hallway in top of the hole. We can have movements from the right or from the left of the hole itself. So
are you also indexing the holes somewhere? I don't remember you did that.
In this map by letter.
But also you need to know the position relative to the hallway, right? Or not?
Yeah, in this one.
Oh, okay, perfect. I did miss that one. Perfect.
So yeah, because I'm using this one to compute the costs of the move.
Exactly, yeah. And you also need to know exactly if you can keep going left or right, depending where you come from.
Yeah. This is not changing the board. This is just in giving you all the possible moves. If this was chess, this is giving you all the possible chess moves that you can do given a board. It's the same. Then we apply a move to the board. We create a new board to return. So we return, we don't change ourselves. We return you a new version of ourselves with the move applied. We copy the cost, we copy the parking, we copy the holes configuration, we copy the depth. Then, if the command is going outside of a hole, we take the animal from the hole. We take the letter of the animal from the hole, because we look at what type of animal it is. We put it in the parking, we put it in the hallway. Then we remove the animal from the hole because we moved it. So we remove it from the hole and we put it in the hallway. So here the whole vector is shrinking by 1 when we put stuff outside. Then we compute the cost of this move. That is the old cost plus how much it costs to move that animal. Based on the map that we have here.
110, 100, 1000.
So the cost of doing that multiplied by the vertical displacement to go from the hole to the hallway, and the horizontal displacement to go to the position of the hallway that we want to go to. That is
exactly. So you're calculating the number of steps and multiplying it to the cost of every single step per the type of animal.
The same if the command is from the hallway to a hole. I take the hole, I put the animal inside the hole. So I take the animal that is this guy here, and I put it in front of the animals that are already in the hole because it goes inside. So it's facing left, basically, of our vector. I update the cost in the same exact way. This is the vertical displacement to go from the hallway in the hole, and the horizontal displacement to go from the position it is in the position of the hole. And I remove it from the parking. I remove him from the hallway because it's not there anymore. After all of this, I return the new board, the new configuration. I define a utility function that gives me the current state, and this is needed in the solution to do an optimization. Here is the solution function. The solution function is something that we already saw previously. So we take a initial state, that is our state in this line. We put that in a stack. We keep utility functions, the utility variables. This is a map of the state that we already saw playing to an integer that is the cost that will be in that state. And here we have our return. We have to find a min. We have to find the minimum. So we start with a variable that is infinite plus infinite. So we go on from here. Now, while there is stuff in this stack, this could have been at the queue. Probably it was faster. I don't care. It's already slow. I take the state from the right of the stack. Why from the right of the stack? Because I try to have at least a first working solution, whatever it is its cost. Because with that cost, I will discard all the states that goes above that cost. Because if I have a solution in my hands that is 30,000, and if I have states that goes above 30,000, it's useless to go on those states because I know that they will not be the winner one.
Yeah. So if I'm understanding what you're saying, you're basically kind of building a tree, but you are building this tree incrementally because every time you basically simulate all the possible moves, but that doesn't necessarily give you a complete solution. It's just from a given configuration, all the movements that you can do in and out, basically.
Yeah.
And then you create all the commands, and you have all these commands in the stack or not? Or in the stack, you have sequences of command?
In the stack, I have states. I have the boards.
Okay.
Then I take the last one from the stack. If it is final, I check if it is less than my current minimum, and I assign it. Otherwise, I take all the possible moves that come from this state. So
that's where you generate all the moves.
Yes.
Okay.
For all the possible move from this state, I compute the new state, doing my state, apply the move, and I have the new state. I compute the key of the new state, that is a unique identifier of the configuration of the animals in the board. So all the position and univoc is important. Then I say, if this solution is less expensive than my current solution, so if this can be less expensive, and I never saw this configuration of the board before, and if I see this configuration of the board before, I saw this configuration with an higher cost. So if it means that I was already configured like this, but with a cost that was higher.
So you are potentially finding a solution that is worth exploring?
Yeah, if I find a solution that is worth exploring, basically this line is say exactly that. I put this board in my scene states. So, okay, I saw this board with cost 100, for example. Because if I go again to this state with a lower cost, I can still try again this state, even if I saw it already. And this is also preventing me, if I see this works also the other way around, if I find this state with an higher cost than the one that I found, makes no sense for me to go on.
And this is also probably preventing you from infinite loops, right? Because you could kind of move the same thing in and out all the time.
If I have a state, I move in, I move out, I move in, I move out, I can go in an infinite loop. But if I have a state that costs 200, I go in and out. At this point, I am in the same state, but with a cost of 220. At that point, this state got discarded because I was already here, but with a lower score. So at this point, being here with a higher score is completely useless.
Yeah, makes a lot of sense.
I add to the stack, and I go on until the stack is empty.
So basically, by popping, what you are doing, you are always taking the latest the thing you push to the stack. So you are kind of exploring in depth at that point. So that's why you are able to complete a game while having explored all the others in parallel. So you complete one, and then you go up again in the tree, try another one. If it's already more expensive,
it's a little bit like backtracing, even if it's not a backtracing algorithm. I start from a solution, I do this free until I have a solution, then I fall back and I say, okay, but if I was going this way, oh no, this way was more expensive. Okay, I'm not going there. Okay, but if from here I was going here, oh, it's still worth. Then here, oh no, too expensive. Okay, let me go back. And then doing this, at one point, you will never have a very big free on the left because the one on the right already had the solution, and when the one on the left has a more expensive solution, you discard. So there is nothing smart here. Doing the moves that seems...
is complaining global state you would like to change. Good luck. I don't know if you have any other suggestion, but I mean, it doesn't seem too terrible conceptually. Then I don't know how it translates in
Rust. This board is functional because this board is not mutating. This board is created and then it gives you a new board. So this board is not mutating itself. It's just giving you a new board. So we are never... with borrowing, this will be funny. We will never use the same board more than once here and multiple times here. Then we discard the old board, but it stay in the stack for a while. Then, there is this stack that is a vector that can grow a lot, but fine. I mean, and we need to create some kind of command because for me, a command was a string. of 3 letters, is better in Rust to probably have a type for this.
Yeah, we can do an enum or something like that.
Okay, this solution works. The results are correct. The time are 7 seconds for part 1, 5 seconds for part 2, and part 2 is just add the 2 rows that the README say to add, and run the same stuff again.
Nice. Okay. Tomas is asking ordered stack. I'm not sure what you mean.
But well, here we are appending on the right and popping from the right. So yeah, is sorted, is ordered. But not sorted. It's just keeping the order we put the stuff in. To be honest, it's just an optimization. Even if I pop from the left, I think it's not taking a lot longer. It was 7 seconds. Let's see. If I pop from the left instead of popping from the right, it's taking 7 seconds, so it's changing absolutely nothing. And part 2 is even faster. I don't know. That depends from depends on the single cases.
Right.
Yeah, but anyway, yeah. From the left or from the right is the same. So even if it's not ordered and you take a random state, probably it's going to work anyway. Yeah, times are not changing.
So Tomas is saying instead of a stack, you can have an ordered queue, and you can avoid to have global state.
I have no idea what is ordered queue in Rust, but fine.
Okay, I guess when we get to the code, we'll get more practical suggestions.
Okay, let's try. So we have a working solution. It's a little bit of code in Rust, probably. I don't know if we will be able to finish today, but at least we can start defining the board and having all the moves out. Then we can write a test that assert that the moves of a certain configuration of the board are a certain list of moves, and it will be something. What do you think?
Yep, sounds good. So should I drive this one?
Yeah, if you don't mind.
Okay, so let me switch. Right, so let's go into here and let's start defining some structs. Let me know if this is too small or if it's readable.
For me, it's fine.
Okay, so let's start by creating struct burrow, we call it. And we have always, I guess, which is going to be, what do we create it? Like a...
That was a vector of animals.
Right.
Do you want to also have the enumeration of animals A, B, C, D?
Yes, so let's do that first. Let's do enum amphipod.
Are you sure? Okay, let's write amphipod.
A, B, C, D.
Nice.
And then basically what we want to do here is
do an array. You can do an array of 11 of amphipod.
Yeah, exactly. We can do...
can you have nulls in...
okay, we can do option of amphipod, right? 11.
Can you do an array of options?
Yeah.
I was not aware of that. I mean, in the old way, there can be in any position an amphipod or nothing. So
exactly. Yeah. So Tomas is saying because you keep, let me show this, because you keep always from the head that we have less consumption. So in this way, you are exploring. Oh, I see what it means. Okay, to have an ordered queue like a heap or something that is based on cost. So you pull the ones with less cost. That could be an optimization. Yeah.
Yeah, that could be an optimization. Also, the Python one, right?
Good point. I didn't realize that. Thank you for the suggestion.
Yeah, I was very brute force.
Yeah, let's keep it simple for now, but this is definitely an amazing optimization that we can also try to benchmark.
I want to try that also with Python. Yeah, not today.
Okay, so we have always, and then we
have one always, not multiple of them.
Right,
so
we have one always. Thank you.
And then we have the holes that are a map of what? They are 4. They are 4 holes.
They are 4, yeah, and the position we can map it somewhere else, right?
They are 4 holes. Yeah, we can map the position somewhere else in a map.
And it's a vec of option of amphipod, or no? We just
vector of vector of amphipod is enough. If it's empty, we don't put anything. Yeah, and there are 4 holes. Yeah, and this describes our state. So that is our state. Then we need the commands.
Then we need commands. So I think we can do an enum command, and command can be in or out, right? Like the amphipod going from the hallway into a hole, or from a hole going out.
Yeah.
Does that make sense to you?
So if they go in, they go from an integer that is the position in the hallway from a usize, right?
Yeah.
To how do we enumerate them? We can use amfifod, but that will be confusing. Because in my solution, I use
it could be usides again, right? Because if we index the 4 of them.
Yeah, 2, 4, and 6, and 8.
Yeah, maybe it makes sense to say not use an enum and just give it names.
Well, the position in the hallway is a usides.
No, I'm just thinking to give it like names to the attributes.
Yeah, names to the halls. That again, they will be A, B, C, and D. But
so will be pos hallway.
Mm-hmm.
And position, all index.
Yes, all fine.
And then instead, when they go out, we have they go from an all index, right?
Yes, to one position in the hallway,
which is usides, to a position in the hallway, and it's usides. Okay, so we have amfifod, burrows, and commands. Sounds good.
We need to parse our input from a string to a borrow.
Let me do a quick thing. Let me do implement amfifod, and we do fn move cost very quickly. And this is basically takes self and it returns usides, and basically match self. And do we need a reference? Oh, I don't think we need a reference. Okay, and we do that, but close enough, Copilot.
Oh, this is magic. So you define a function in the enumerator, in the enumeration that takes the enumeration as parameter, as a reference, because we don't want to get it. And then based on that, okay, I got it.
Yeah, so I think this is kind of a static way of, because they are just stored in the enum, so they don't get copied all over all the time when you create new instances of the enum. Or at least this is my understanding. Please correct me if you think that's wrong. People in the chat. Beautiful people in the chat. Okay, so similarly, can we do, I'm wondering how can we store instead the position of the halls?
The position of the hall is indexed by 2 plus 2.
Index, okay.
The hall in index 0 of that array is in x 0 multiplied by 2 plus 2. The one in index 1 is 1 multiplied 2 by 2, 4, and so on.
If it makes sense to implement that in the burrow, or if we can do a freestanding function outside. What do you think?
I'm not following you, sorry.
Okay, let's cross that bridge when we get there. When we will need to get that index, we'll figure out what's the best way. Okay, so what do we do next? We need to do the parsing, right?
Yeah, I would like to parse the string into a borrow object.
Do we do the usual from string in borrow?
I'm fine if you like it.
So implement from str for borrow. And please give me autocomplete because I can never remember all the missing members. We always pretend there will never be errors, that the input is always amazingly good. Now, here, what do? We will have a string that looks like this, and we will need to come up with an hallway, which, of course, initially is probably going to be empty. So really what we care about are these
from there
values.
Yeah. And A go in the vector in index 0 of that halls vector. C go in the first position, so it's pushed to the vector in index 1, B go in the vector in index 2, and A goes in the vector of index 4. Then you go to the next line and you do the same until you reach line 5.
Yeah, so basically one simple way that we could do it is that we skip the first 2 lines.
Yeah.
Because we know this is always empty and this is always 11. Then we go here, and what we need to read are specific characters in the string, because this is always fixed length. So we need to read the position number 3. 3, is it 3? 0, 1, 2, 3, 5, 7, 9.
9. And if you find a sharp, you are done, because it means that you are
at the end to the last line.
Yeah. So this will be also fine for part 2, if we do the parser like this.
Okay, perfect. So let's start by creating the hallway. Let hallway, and this will be always the same because it's basically
an empty.
Actually, we can define it as that, and that. Thank you, Copilot. Oh, wait. I didn't like it. Because we need to implement a bunch of stuff.
What we need to implement?
We need to derive, debug, I guess. Why not? Clone. What did I do wrong? Arch comes first. Okay, no? Oh, it needs to have copy as well to be able to do this. Interesting. I didn't know. Well, I guess, why not? Should be cheap to copy.
It's an enum. I hope it's not a problem to copy for values.
Perfect, okay. Because I think it just creates the first one and then copies it all over.
But it's very inexpensive. Okay, this is fine.
And this is fine, but this needs to be mutable because we will be...
But the vector inside must be mutable. But yeah.
Then maybe this doesn't need to be mutable, I guess.
Oh, let's try.
Back new, why is complaining? Marker copy is not satisfied. Okay, okay, so we cannot do this. But to be honest, what we can do is, I don't know if anyone in the chat knows a better way. I'm going to be doing something ugly with a comma.
Yeah, because otherwise it's the same vector. It's not 4 different vectors.
If you know any better way, let me know.
Yeah, this is working.
It's not too bad with just 4 items. Okay,
if they were 100, yeah.
So what we want to do is input, which is S. We want to do lines. Then we skip the first 2, right? Skip 2, I guess. And then what we want to do is for every line...
WGAFA is suggesting to do what we did before. The problem with your suggestion, WGAFA, I think that the vector new needs the copy trait, and it doesn't have it for some reason.
I don't know if we can add copy, because we added copy to Amphiphod, right? I don't know if we can add copy to vector. I don't think so.
So nothing, but it's fine like this. Come on. Okay, we skip the first 2 lines. Then for each of the other ones, what we do? We have to take specific X.
Yeah, then we need to... I'm trying to think.
There is each.
Or we can just do a regular for, you know what? For and we also do we need an enumerate? No, right?
No,
doesn't
just
matter.
Push.
So we have for line in this, right?
Mm-hmm.
That should be it. And then basically what we do is okay, now I'm curious to see if Copilot is right.
No, I don't think so.
Split white spaces. No, I don't think so.
No. He's already wrong.
Okay, let me just do a quick thing. Let all positions equal to, we said that we want 3, 5, 7, 9. Yeah, that was good. Good suggestion for Copilot. So now what we want to do is for pos in all position. What we want to do is if S line char's position unwrap is different. Well, if it's equal to sharp, we break, right?
Yeah.
So all of that we break.
But we have to break the outside loop, not the inside loop.
Do you do break too?
You can do that in Rust.
I have no idea. How do you break the outer loop? That's a question for somebody who knows Rust better than us. Can you do labels like outer something?
Oh my God.
Break outer.
Do you want to do a go-to while you are there?
Yeah, I have no idea if you can do that. Let's see.
With level, it's a Tommaso.
Okay, what's the syntax?
Level. Is level or level? Because you wrote level.
How do you specify?
Label. Okay, sorry.
Label. Okay, yeah. How do you specify a label?
Good question. Don't know.
Let me search on Google. Rust break loop with label.
Then you do use a go-to.
Pretty much. Okay, cool. So
pretty much. No, please.
Yeah, this is very close. So we can do outer, I think. If I'm reading this correctly, and then break outer. It just needs the tick. Okay, it's not happy because we are not returning anything, right? At the end, we need to return a new sum. Okay, of a burrow with all weight and all.
Okay.
Okay, so of course we are not filling anything, so we need to do that. So here, I think that we could do here is to implement from char.
Mm-hmm.
From
for the amphipod.
Char. But we should probably do like a try from. But for now, yeah, I'm going to just use this nice implementation from Copilot. Thank you. Because, of course, if there was another character that wasn't A, B, C, or D, this will panic. We kind of trust that that's not the case because we control the input. So what we can do here is basically get the amphipod. So let amphipod of type amphipod by doing, actually, let me do this. Let char equal this, and then char, and then basically we can do char.into. So at this point, this will be an instance of amphipod based on the character. And now, what we can do...
I think you need to add, 3 goes into 0, 5 goes into 1, and 7 goes into 2, and 9 goes into, 3. So the formula is not position sliced 2.
Mm-hmm.
The formula is do a tab, then we change the formula in the index. Accepted, okay? Is position minus 3 sliced 2. So you have to put round brackets around the position and minus 3, and slice it by 2. This means that we'll have a mapping between the position of the holes and the index in the array.
Now it doesn't like this one because we need get mute, I guess. To be able to do push. Is it gonna work?
Oh, you have to put mutable in line 49.
Oh, because this is an option, so we need to do some.
Okay. Why is it optional?
Because they might go in and out. Do we?
Yeah, but those are the holes. This is not the hole with this one.
Wait.
Holes is a vector of amphipod. It's not. There is no optional in holes.
Yeah. So what was the issue? What are we getting? No method push for std option.
You have to unwrap the amphipod.
Cool.
No, it's not the amphipod that you need to unwrap.
No, we need to unwrap the vector because, of course, it's not guaranteed that there is a vector at that position.
Oh, okay.
Now, why is it complaining here? Let's figure it out. Cannot borrow holes as mutable. It's not declared as mutables. Okay, perfect. So we needed that. And now it makes sense.
Okay, so we are getting that one, that index, unwrap it because it could be an option, and then we push to the... But it's an array. Why you need to unwrap when you get from an array?
Because you might go out of bound.
I want a panic. I'm fine.
I guess if you want a panic, but I don't know if that would work.
But just with square brackets, is not. If you just put the square brackets, it's not working. Remove also one round bracket. You have one extra round.
Oh yeah, there. That works. That's because this one is mutable, but I wasn't sure we could do that with the mutability.
Fine, works. Okay, I mean, it's impossible to go outside. We know that the array is 4. We have 4 elements in that array. The numbers are those ones.
Again, this makes sense only because we are controlling the input. If this was a web server where people would copy paste their own inputs, probably would make sense to be a little bit stricter and check all the boundaries and all the parsing. Okay, so let's test that this makes sense.
Can we write? Can we write a debug of borrow?
Yeah, that's what I was going to do. So what we can do is look at that. I'm tempted. Doesn't need to be mutable, right? And then we can do dbg of borrow. And at this point, why doesn't it like it? Oh, because it doesn't implement. Debug. Oh, we only added here in the amphipod. Good point. In the
enumeration.
There you go. Debug. And derive. I wish that this was shorter.
Lowercase d.
Okay. So now run this part 1 test. And what did we get? Let me make this a little bit bigger. So always we have empty positions all the way through. And also we have AD, CD, BB, AC. Does that
I think
make sense?
Is the right when the input.
So it's AD, CD, BB, AC. Correct.
Cool. So we are parsing correctly.
Woohoo. Good first step. Okay. So what's the next step then?
I think the next step is generating all the moves.
Mm-hmm.
So we need a function that takes a borrow and they give you back a list of commands, a vector of commands.
Okay. Where do we do that? Do we do it in the burrow as you did? Like you did like a class? It could make sense to do.
It was in the class in the board. I called it board, but it was my borrow class.
And what we can do is just moves, and this one returns a vec of commands, right?
Mm-hmm.
Cool. So let move the Autopilot. I mean, I like the first one, but cool. And then here we return moves. We need to fill all the moves.
Yeah.
Stop it. You have no idea what you're talking about. What is command move? Come on, Copilot. We don't have that.
Command move. Now we have to create one of the two. So what we can do now is focusing on the amphipod going outside. So for all our halls,
simulates amphipods going outside. So this is basically for
all of our halls. So
by the way, this
self. Okay,
self,
yeah, we do the self.
For self halls. For all in that.
Self halls.
Self, yeah, I have no idea how that happened.
Why doesn't like for everybody?
Cannot move. Okay, sorry. I still need to get used to when to use references or not.
But isn't self already a reference? You want halls as a reference. Self is already a reference. Oh my god.
Oh, Tommaso is suggesting something that it's interesting, I think. Why halls is a vec and not an array?
Because we don't have to declare, because we have part 1 and part 2 with different depth, so we don't have to declare in this way.
We could use cost generics, but we could probably do that as an optimization later.
Yeah,
like we could have here sides, something like that, like all sides. I don't know.
But we are using the number of amphipod in the hole for the cost later, and in that way, it's just the size of the vector, the number of amphipod in the hole. If you do an array, you have to have an array of optional amphipod, and then you have to look how many of them are not known. Yeah, you can do the same, but well, let's try now with the vectors. If then we can move to arrays.
Yeah, I think it's doable with const generics and doing another array of option ampipods. But I mean, let's keep it simple for now, and then we can see if there is a performance improvement in going down that way. Because of course, arrays are always allocated in the heap, right?
Yeah.
Cool. So I got lost. Where were we? Here.
We are doing the for all the hole. If there is something in the hole.
If all is not.
If the hole is
actually, I kind of like that. Is empty. Continue, right?
If there is nothing to get out of this hole, continue. Yeah.
But wait, stop.
Where are you?
Okay, then this means that it's not empty. Okay, so what do we do?
Now, if not all of the amphipod in this hole are the right one.
Okay, we need a map for that, right?
Yeah, now the index 0, we can do an enumeration.
So here we did an enumerate, yeah. Enumerate, and we do I PDX.
Yeah.
Do you need either? You need either. And why not? What's the problem?
You don't.
Also is not an iterate. Oh, because wait.
Also is an array.
An array. How do you enumerate over an array?
No idea.
I'm quite sure. Oh, remove the ampersand. Thank you so much. Okay, good point. And now we have index. Okay.
Yeah. Now we have to continue also if all the animals in the hole are the right animals. I mean, if the first hole is full of A, we are fine. We are not removing an A from here. So
yeah, we just need to store somewhere this hash map, right, of indexes with the correct position where they go. Like A goes in the index 0, B goes in the index 1, and so on, right? should we do in the amplipod itself? Can we do fn
desired home?
I like it. Desired index.
Oh, yeah.
Self, and it returns a usides, and perfect, brilliant.
This
Thank
time is
you,
correct.
Copilot. You are showing all your value sometimes. Okay, so what we want to do is if all either every is there every? Look at that. No, don't push.
Continue. No, continue.
Why doesn't like every? Is it all? All, close enough. Okay. So basically, if it's empty, don't do anything. If they are all sorted, all kind of properly filled, don't do anything. Next case.
At this point, we have to do something. What is this something? This something is getting a pointer. In Python, I started with a pointer pointing to the current X position. So if this was the first hole, this position was 2. If this was the second hole, the position was 4, 6, and 8. So is the index our starting position? Is the index multiplied by 2 plus 2?
Index multiplied 2 plus 2.
This means that the first hole, that is index 0, goes as an x of 0, the sec 4, 6, and 8, like this. Now, from the start, we have to go left. The start going left, okay?
Okay, going outside. So this is simulate going out and left, basically. This is a deliberate choice. We want to try left first.
Oh my God, what is?
Let's ignore.
Okay. Now, we do a let mutable position equal start.
Yeah.
While the position is greater or equal to 0.
Okay.
Greater equal, not just greater, because position 0 is still a position we can go to. If the hallway in this position is not known.
Okay, close enough. I don't think we want all of that yet.
The break, keep the break. Yeah, but he's not. Is
some. Well, we could be. Do we need it? The position? Well, do we need the hallway cell, right? Or no? No, it doesn't matter because we are just going to.
If we bounce it into somebody in some animal, break. There is no way we can go further left.
Yeah.
Right. Yeah. After the if, after the break and the if.
After the break, do we need this post -1 now, right?
Yeah, we need that one, but before that one, between the curly bracket, yes, there, we have to say, if this position, here is hard because we have basically to add a command to the vector of moves now. So we have to do a moves push, but only if the position is not 2, 4, 6, or 8.
Okay. So we need that information somewhere.
Oh, you can do if position is not 2, 4, 6, or 8.
If pos
different from 2 and is different from 4 and is then there is probably a better way of writing
this. 6 and 8, yeah, perfect. Command move, that's not what we want, but close enough.
Our command is called going out. This is going out.
And then we need to pass 2 things. Okay.
What were the 2 things? I don't remember.
Here, the autocomplete could have been better.
It's called command, or?
We call it, where is it? Did we delete it?
Lost it?
Oh no, burrow, it's below, that's why. Command out, and these are the 2 values.
Okay, all index is our start. And the position in the always is the current position.
Is pos.
Good.
Why so didn't like that? Wait a second. Expected a function.
Do you have to use the curly brackets?
Oh, I see why. Yes, that's why. Good point. It's like a struct at that point.
I think you throw in a triple equal somewhere. Okay.
Also, why doesn't like this? Comparison involve the minimum or maximum element of this type. What? Absurd extreme comparison.
POS is unsigned.
Is a U size.
Make it signed.
But then we'll need to do everything
as I size. No, but well, you have to do a casting somewhere.
Okay, let's do it here.
But it's only needed for going left. So,
but then you cannot index by I-sides.
Okay, we have to go left, and we don't have to go negative. Line 64, probably you have a type.
Line 64, yes, I have an extra. Okay, don't tell me that I have to do U sides again, because I mean this is a solution, but it's ugly. And
also 75, you have to do as U sides. 75.
75. Oh yes.
Basically, I want to decrement an integer until it's not decrementable anymore. But obviously, it must be integer on its own. But well, this is working. Let's go right. Now let's go right.
By the way, Thomas is suggesting something smart. I think it's like, why don't we just do if position modulo 2?
Because 10 is a valid position. And 0
also. Right.
0 and 10 are two valid positions.
So it's probably better to be explicit rather than excluding those two cases and do a generic modulo 2.
Yeah, 0 and 10 are valid, and we will put stuff there. So
okay, now, so at this point we are
right.
creating commands of things that can go out and go left.
Yes, now we have to look at stuff that can go out and go right. So position is
one thing that I want to clarify is because we go from start and then we start to move to the left, this break here makes sure that we don't basically skip over, because as soon as we hit into something, we stop.
Exactly.
Okay, cool.
Now we have to do the same going right. So position, you can set it to start again, because position now is again start.
Simulate going out and right. Copilot, do the magic.
We already have position. Can you declare it? Can't you just decipher it?
Equal. Wait.
Here, a U size is enough. We don't need an I size. U size will be enough.
Then do we redeclare it?
Can we redeclare it?
Yeah.
It's not
it's equal to start again, right?
Yeah. Not complaining. Perfect.
Oop.
Instead. Now, while PTR is while our position is less than the length of the hallway, yeah, correct.
Mm-hmm.
While it's less than the this is basically what we wrote before. If we find somebody, we break. If the position is not those one, we go out and we go right, and then we do POS plus equal 1. This time, Copilot was smart.
And I want to double check it again.
Yeah.
Start and pause, and it's +1. Okay, cool, makes sense.
Now,
do we check that we don't? Oh, okay, when you go out, you cannot, like, you are moving from your own position, so you don't have to check your own position, right?
There will be nobody in queue.
Mm-hmm. Another thing, we never move. We can only move in and out. Like, we never move linearly in the hallway, right?
No, we never move hallway to hallway. It's in the rules. If you take a look.
I didn't remember the rule, but it's good to clarify that.
Now, outside of the loop on the halls, we have a loop on the halls. Yeah, outside of that loop.
Yeah, we need to simulate from the hallway to go inside, right?
Yes, exactly. So now, for all the stuff in the hallway.
Okay, so for all the items in the hallway, basically, that are not empty.
Yeah, that are some.
So for look at that, almost.
It's a lot of code.
I think it's close, but do we need the index? We do need the index, yeah.
Yes, we need to know where the amphipod is, because it's our from.
In self hallway dot iter dot. Well, I guess we can check later if it's empty or not. I was thinking to do like a filter here, but it's probably easier to just.
You can do if amphipod is known, continue. Why? I don't know. Because you forgot to enumerate.
Good point. If amphipod is known, continue.
Yes, we can't put it in if he's. Now, we need to know where the amphipod wants to go. That was the function that you created. I forgot the name. Desired home.
Yes. So we need to unwrap, and then we need to say amphipod desired home. So that's the index where
that is the index where the amphipod wants to go.
Mm-hmm.
Now,
do we always try to go to the desired home, or we can also try to go somewhere else?
No, we just go in our desired homes if we are in Norway. They don't go in somebody else's house, from what I know.
Okay. Line 100, we can use a match.
Where?
Fair point. Here we could say match amphipod some A, do something none. None would be break, right? I don't know if it's more readable though. And of course, ignore all of this. We need to move all the logic we are writing here inside there.
I don't think it's way more readable, to be honest. We can do that later if there is some performance gain, you think?
I don't think so. No, but I think the other approach keeps the logic more linear, which I like it. But it's probably less rustonic, if there is such a word. Rustic or oxided, I don't know. So this is where we want to go, right?
Yes, but the index, so it's 2, 4, 6, and 8, right? What is giving back? 0, 1, 2, 3, or
the 0, 1, 2, 3, yeah.
Okay, perfect. So now the logic here is if the hole you want to go in is empty, or is full of animals of your kind, and there is nobody in the hallway between you and the hole, at that point you can go in the hole. So we can split this condition in two. Is the hole empty? Is the hole empty or full of people of your kind, of animals of your kind? And there is nobody in the hallway between you and the hole.
So if it's empty, then what?
The desired hole is an integer. No, it's I'm
already reading.
Yeah, you already the reference. Okay, if it's empty or what was desired all.all, okay, .iter.all. If they are all of your type, they are all amphipod like you.
.iter.all. No, Copilot, calm down.
Well, if you have the same desired home, you are the same amphipod, but that's also
true. I'm thinking that now we cannot easily compare without creating an equal, without deriving
equal. Derive equality. I mean, you can tell if A is A. You just need partial equal, or
partial equal should be enough.
What is the difference between partial equal and equal?
I think one can tell if the one is bigger or smaller, while the other one is just if they are the same. Correct me if I'm wrong.
We just care if they are the same. So
let's see if that's enough. So what we want to do is if A is the same as
amphipod,
is that going to be enough? Doesn't like it. Partial equal is not. Oh, because one is a reference. Which one is
put a reference in front of the one on the right and see if it's
a reference here.
Yeah. Okay.
And now why is it complaining here? Cannot move out. Why are we moving out?
Are you moving
out? Because we want a reference there. Yeah, because otherwise we are moving.
Out of the array. Okay. Yeah,
we are moving ownership of that value inside the array. We just want a reference.
Okay. The condition is again if this and.
By the way, Tommaso is clarifying that it's about absolute ordering. So partial equal, I don't think is concerned with ordering, if I understand correctly, while equal is also concerned with ordering. Okay. We'll try to clarify that, but this is our best guess right now.
Okay. We have to go in the hole if the hole is empty or is full of our kind, And there is no, so you put these two conditions in round brackets.
These two in a round bracket.
And then we do and. Now we have to find a way to express there is nobody between us and the hole. So it means that all the slot of the hallway between our current X, that is IDX, and the desired home index, that is the one inside the square brackets there, they must be all known.
Okay.
But we can be right or left of the desired home. So.
Oh, that's where you did that slice thing.
There is where I did the between. So a function that gives me a slice of the array between my current IDX, that is my current position, and my desired position. That can be obviously left or right of me.
Okay, so how do we do this? Do we want to implement the same?
Let's implement between.
Okay, and we implement it as a new function, right?
In the borrow, yeah. Inside we can implement more than a function, right?
I think
the
so.
same impl borrow. So
FN.
function between. Then you can change the name. Reference to self. AAB is fine.
Okay.
Now,
I don't know what it's doing.
No, it's just if B is greater than A, we return a slice of the hallway. So
okay, we want to return
a slice of that. How do you return a slice of array?
I think it's like this, and then what do we have? Option amplitude.
Yes, option amplitude for this.
Now it's probably going to complain about lifetimes, unless we're lucky, but let's see.
Self hallway.
Return self hallway. Is that what we want?
Between A plus 1, because and not including B.
Okay.
Instead, if at this point B is less than A or A is more than B, we return from B without the plus 1 to A without including A. Perfect, like this. Is that
include? Okay. Okay, it's guessing the lifetime. That's amazing.
Okay, so back to our if. That this way we put some logic outside of it.
Now, where was it? There.
Line there, and between
self
IDX
dot between
self. Yes, sorry, self dot between IDX. And you didn't save it in line 114 the desired home index in a variable.
Desired no.
Save that in a variable because we need that now.
IDX, I cannot type anymore. And this one.
Blame the keyboard. Blame the keyboard. Always blame the keyboard.
Okay, I'm also gonna do this distantly.
Oh my God. What are you doing?
Because we call it decided there.
Okay,
and self between IDX and
the desired home index. Dot iter dot all was suggesting you similar, but is known. Perfect. And they are all known, and they are all empty.
Okay.
So if there is nobody between you and your destination is empty or is full of amplitude of your same kind, at this point we add to the we can move. So we do moves push command in because we go in this time. The whole index is our desired home index, and the hallway is the desired home index is
we need to decide whether we keep this flat and we compute the X position later.
I prefer to. We have to decide if the command, but also the between is not working like that. We need to do between because the decided home index is 0, 1,
right,
2, or 3. We have to do the formula to get the real X. So, nice. Create another variable between 114 and 115.
Okay.
Desired home X chord. Yeah, that is exactly that formula that we just change the name to the variable
X,
and use that in the between. Use the X in the between in line 120 instead of the index. You use the X, and now for the command we have to choose. It's easier for calculating the cost if you use this in the command, in my opinion. It also makes sense with what we did before.
Okay, let's do a few things. Let's rename. What did we do? The commands there. So
all X, you want to call it?
Yeah, let's just call it all X in both cases. Rename symbol, I guess.
Do you think it's working?
I think I did it before. Okay, and we also need to fix the other one, though, right?
Oh, the other one, I think we were already reasoning on top of positions only. Yeah, you see the start is the index multiplied
okay,
by
perfect.
2.
So now it's correct. Should we just...
Now,
okay, no.
Change line 125.
I am going to be picky. Sorry. Because they're calling it everywhere else. Okay, change
again,
line
125.
125.
You
and
have to use
decide
the X.
X.
Yeah, okay. Cool. Now, this is enough. Try to call it with a debug, then we can write a test for this. In theory, starting from an empty board, we should only get out commands.
Starting from the initial state, you mean, right?
Yeah, we should only have out commands.
Another thing that I'm realizing is that in this thing, we didn't add any cost.
Oh, yeah, we forgot. Yeah.
So let's quickly do that as well. And of course, initially, the cost is 0. Where do we do the parse? There. Okay, so now what we want to do is to debug this one. And then we also debug the moves.
Borrow moves, yeah, and see what we have there.
We didn't implement for command. Good point. Where are the commands? We probably should do a library at this point, but whatever. We can refactor in a second. Okay, so run part 1. Okay, so we have, let me pull up the input as well. So let's see what kind of moves it's suggesting. It's suggesting to go out from X2, which is this one, and go in position all the way 1, which is, why is it not going to 0?
It's going 0 to the line below, because it's going left.
Oh, it's just doing the first step left. Yeah, it's not just stepping outside and staying there. It's just going left.
No, because...
Okay. Then the next one is X2, still going out from this one and going position all the way 5.
Because it's not going in 4.
Is going right at this point.
Yeah.
Okay, so it's going here, basically.
This is
and then we will have the same for this.
5, 7,
and
9, and 10.
10, yeah, there it is. And then we have X4, which is C. And C can go all the way to the left and all the way to the right. So C is 3 and 1, or 0. And then it will, when it goes to the right, it's 5, 7, 9, 10. Similarly for 6, which is A here, it can go all the way left. So 5, 3, 1, 0
okay.
Is the B, yes. And all the way to the right, which is 7, 9, and 10. Now the last one we see, which is this A here, can go to 7. 7?
Yeah, left.
Is it this one, 7?
No, that is 9.
Yeah, so why 7?
Because it goes left.
Oh, yes, okay, so it's going here and going all the way left. Sorry, I was thinking right. So it's 7, 5, 3, 1, 0. And now right is only going to 9 and 10. Okay, perfect. So that looks correct.
Now we could implement a move or call it a day.
What time is it? I think we should call it a day. We have done about 1 hour, so 1 hour and a half.
The streaming is say 1 hour and 42 minutes.
Yeah, so definitely.
With 10 minutes of intro, yeah.
Yeah, sounds good. So I'm gonna wrap up. Yeah, go ahead.
Just to wrap up, what's left to do is to implement the moves so that we can give a command and we get a new board, a new borrow out, a new state of our stuff. We have to implement a isFinal that tells us when the board can't move anymore. We could probably use moves.
Or at least it shouldn't move anymore. Like everything is sorted. Everything is completed.
We could make the moves an optional vector, and if it is complete, we don't evolve anymore, and we don't give any new moves, well, we can discuss. And once that is implemented, we can write the solution itself. That is this.
Well, to be fair, if it returns an empty vector.
Also.
Yeah, you don't need to make it an option. Yeah.
And if you have no more moves, it means that this state is final. Cool. And
but can there be like a difference between final because you cannot move anymore because you're like stuck, and final because it's actually already sorted correctly?
Yeah, there could be. So
probably you should still check that it's actually properly sorted. Because in one case we are assigning the minimum value, assuming that it's the minimum. In the other case, we just discard that state.
Yeah. So it's better to have a function that tells us if we are done. Okay, we will write it. Again, apply moves, a function to returns a boolean that give us if we are done, and then we have to implement the loop with the stack.
Yes.
Next time.
Perfect. Okay, and we're probably going to do a little bit of refactoring with creating a library because there is already too much code.
Yeah, there's already a lot of code here.
And so then we'll probably, after that, if everything works, we'll follow a few suggestions that we got today, for instance, from Tommaso, to use like a priority queue to, when we have a stack of possible moves, try to keep the move that has the minimum cost, which is probably optimizing for finding the cheapest solution first.
Yeah, I will try to do that also in Python. I'm curious. But let's wrap it up. You can find the recording on YouTube. The link is on the Twitch channel in the About session. If you're watching this on YouTube, we do live streaming on Twitch every Monday, 5 p.m. and half, 6 p.m. Dublin time. Make sure to check the Twitch link in the YouTube description. Give us a follow so you can be notified. The bell icon, all those kind of stuff that YouTubers know. Feel free to leave us comment and open PRs. The repository of code is on GitHub. Everything is well accepted. We are trying to learn Rust, so don't expect our solution to be beautiful, but they work typically. If you know better ways of doing stuff, please tell us. Thank you for all the suggestions and the collaboration in the chat. And are we going to rate somebody? Is somebody online?
Yes, we are rating somebody. I don't know if they do Rust, but they generally do nice coding related stuff. So hopefully you are going to enjoy that. So see you next week, probably. Bye, everyone.
Bye.